Okay, so let's formally define then what, if I given two functions f and g, how I can identify that they're in fact inverses of each other. So if f is a one-to-one function and g is the inverse of f, then what that means is that f of g of x should simplify down to x, and consequently g of f of x should also simplify down to x. Okay, so we're going to use that idea and test to see if the following functions are in fact inverses of each other. So that means we need to do f of g and g of f of x, both compositions. So we're going to start with f of g of x. So in this case, who is the outside? That would be f. So I'm going to set up the outer function and sort of leave a blank. And what am I going to put in what's the inner function? That's going to be g. So that's x minus 2 over 3. Okay, so then we're going to try to simplify this. So order of ops, multiply by 3, divide by 3, so it leaves me with x minus 2 plus 2. And I can see very quickly the 2's are going to cancel out, and I'm left with x. Okay, let's go the other direction. So g of f of x. Okay, this time g's the outer. Okay, and what am I going to fill in that blank with? I'm going to put that with 3x plus 2. Okay, and of course, order of ops, what happens? Plus 2 minus 2 cancel out, and we're left with 3x over 3. And that, of course, simplifies down to x. So at this point, what can I say about f and g? I can say that f and g in this example are inverses. Okay. Now another sort of interesting observation to make, look at the order of ops when we did the simplification. So when we did f of g, notice we multiplied and then subtracted, and that's how we got our simplified form. When we did g of f, we subtracted, then we divided. Okay, sort of did the reverse order of what f and g did to each other. So a lot of times when you're dealing with inverses, you should see something like that. Let's look at the next example. So we got f of x is 1/4 x minus 5, and g of x is 4x minus 20. So we'll start with f of g of x. Okay, so our outer function is the 1/4 x minus 5. And so what am I going to insert inside that parentheses? That's going to be 4x minus 20. Okay, alright, so in this case, distributing would make the most sense. So 1/4 times 4 is x, and 1/4 times 20 is 5. So 4x, or x minus 5 minus 5, and we get x minus 10. Ooh, any way for that to cancel out? Nope. Okay, so let's take a second then. What does that actually mean? That means that f and g at this point are not inverses, so it doesn't even make sense to even try switching the other direction. Nope, because they both have to simplify down to x. So f and g are not inverses. Okay, and our last example, so we'll jump to f, oops, be consistent about my colors here. F of g of x. Okay, this time who's on the outside? That would be f. So that's 2 over something minus 5. And what am I going to insert in that blank? That's 2 over x plus 5. Okay. Alright, so let's look at our what's next then. So the plus 5 and the minus 5 cancel out. And I'm left with 2 over 2x. We got to think for a second. Ooh, what is that rule? If I'm dividing by a fraction, I want to multiply by its reciprocal. So it's 2 times x over 2. And what happens to the 2's? That cancel out and I'm left with x. Okay, so let's go the other direction. G of f of x. Okay, so we want g on the outside, so 2 over something plus 5. And what goes in the blank? Well, that would be 2 over x minus 5. Okay, so we just actually practiced this. If we're dividing by a fraction, we want to multiply by the reciprocal. So that becomes 2 times x minus 5 over 2 plus 5. And what happens to the 2's? Yeah, they go away, they divide out. And we're left with x minus 5 plus 5. And of course the 5's cancel out and we're left with x. Alright, so what does that tell us? That tells us that f and g are inverses. Yay! Okay, so now that we've kind of practiced identifying if two functions are inverses, let's actually go about writing our own inverse. So the process is like this. We're going to kind of highlight this as I pointed out. We're going to change any f of x to a y. Then we're going to switch x and y places. Solve for y, and then replace the y with the inverse symbol. Okay. Just sort of a word of caution, this f of -1 is we don't refer to that -1 as an exponent. That's just the universal symbol for inverse in this case. Alright, so let's jump into this first example. So we're going to swap out the f of x for y. And then we're going to replace x and y places. So x equals 2y plus 7. Then we are going to solve for y. So in this case, I want to subtract 7 from both sides. And then I want to divide everything by 2. So I get x over 2 minus 7 halves. And that's going to equal our inverse. And that's a perfectly good inverse. Okay, next example. Again, swap out the y, f of x with the y. So y equals 4x cubed minus 1. Then we're going to interchange x with y. So x equals 4y cubed minus 1. We'll add 1 to both sides. Then I want to divide everybody by 4. And in this case, I'm going to keep it, I'll keep it as one fraction. So I have x plus 1 over 4 equals y cubed. And so how do we get rid of the cubed? Well, we're going to take the cubed root. So I get the cubed root of x plus 1 over 4 equals the inverse. And that's a perfectly good inverse for right now. Alright, last example of this. So replace the f of x with y. And then we're going to swap places. So y equals 2, x equals 2 over y. And then I want to solve for y. So I'm going to multiply both sides by y. So that gives me yx equals 2. Now I want to get y by itself. So I'm going to divide both sides by x. So that means 2 over x is the inverse of this. Just so happens to be the exact same thing that we started off with. Okay, so we're going to illustrate sort of a classic problem when it comes to inverses, and just something that it's really easy to overlook if you don't have a brief conversation about that. So let's start with just graphing y equals x squared. So we're just going to come up with some general ordered pairs here. So we'll look at -2, -1, 0, 1, 2, and I want to square all of that, generate those ordered pairs. So we get this lovely graph here. Okay. Now, is our original graph a function? So does it pass the vertical line test? That is a yes. Is the original graph 1 to 1? And the answer is no. It does not pass the horizontal line test. Okay, well that's a concern, but we'll just keep going here. Inverses. So to find the inverse of a graph, we just want to switch ordered pairs. So 4, -2, 1, -1, 0, 0, 1, 1, and 4, 2. So when I plot those points, let's see, 4, -2, 1, -1, 0, 0, 1, 1, and 4, 2. Okay. Is the inverse a graph? Oh, sorry, is the inverse graph a function? It's actually not. What's the concern? Well, it does not pass the vertical line test. Okay. All right, let me try to write that a little nicer. Vertical line test. So it's actually not a function. But we kind of knew that going into this. We knew the original picture was not invertible because it wasn't 1 to 1. So a lot of times whenever you have something like this, we do what's called a domain restriction. So you'll see this extra statement that comes up here, and I'm going to switch colors so you can kind of see the difference between the two. I'm going to limit x to being greater than or equal to 0, which means I'm going to focus in on just that part of the graph. And if I do that, is that piece a 1 to 1? Just that one single piece? And the answer is yes. But when I do that, what is that going to eliminate out of my pictures? That's going to eliminate, or that's just going to give me those ordered pairs there. And so in my inverse, I just have those ordered pairs, which is going to translate to that top set of points. So are those, is just that the highlighted piece, does that still count as a function? And the answer is yes. So a lot of times when you start off with something that's not 1 to 1, you can do a domain restriction on it and generate something that is 1 to 1. And so sometimes in your homework, you'll see problems that have this extra domain statement on there. And the reason for that is because the original function for whatever it was not something that was a 1 to 1 to start off with. Okay, so I do want to end with some good examples of sketching inverses from graphs instead of having to talk about domain restrictions. So when I'm given some sort of image that I need to find the inverse of, what I'm going to do is I'm going to go through and find the ordered pairs, or define it by a couple of ordered pairs. So I can see, for example, that would be -3, -1 is one ordered pair in the graph. And this is 0, 2 is another one. And then 6, 4. And so to find the inverse, I'm going to switch the order. So -1, -3, 2, 0, and 4, 6. And then I'll just plot those points. So -1, -3 is down there. 2 zeros right there. And 4, 6 is right there. So if I connect those points. And if done correctly, it should look like it's symmetrical about the line y equals x. Which kind of goes back to that, if two functions are inverses, then f of g of x should simplify down to x. Last sort of visual example. Here I'm given a nice line, so I just need to come up with some ordered pairs. So I'll just kind of look at a couple of places where I can see it crosses at grid lines. So that would be -3, -1, 0, 0, and 3, 1. And so the inverse, switch the order of those points, and then just plot those. So -1, -3 right there, 0, 0, and 1, 3. And then sketch that in, and of course it should look like it's symmetrical about the line y equals x. And it does. So we did that right. Yay!